Good afternoon. My name is Scott Greenwald. I'm in a group with William Rolke and David Touvell as well, and this is our demonstration of our project for computer communications. Really quickly, this is the author and the article that we will be trying to replicate the simulation. Basically, what this paper was doing was they were implementing an E-cubed MC, or energy efficiency via elastic multi-controller software defined network. And what the authors wanted to do was to find a way to minimize the amount of power consumption needed in order to route data from the original location to its final destination. So throughout this project, we've kind of worked through and stepped through this research paper to determine exactly what the authors were doing and trying to figure out the pieces that were missing and implement their entire simulation to see if we could replicate their results. So just as a quick diagram, and then I'll jump into our actual simulation, the authors went into three different types of network topologies. On the left, we have a 2N tree, in the middle we have a fat tree, and on the right we have a B-cube topology. So our simulations replicate all three of these. Figures B and C are used for a higher bandwidth networks, but the 2N tree runs significantly faster in the simulation. So I'll be running this as our demo and just showing bits and pieces and figures showing that the other two work as well. So to get into the actual simulation, we decided to use MATLAB in order to replicate their process of how they went about with their simulation to get their results. So over here in our run sim function, this is our top level function where the user inputs in what type of network topology they want and what type of traffic they want to use. Right now we're able to either replicate a real traffic situation, which the authors weren't able to describe exactly how they did this function, or we can generate a Poisson traffic where basically everything is randomized, where the destinations and originations of all the sources are. So for this simulation, we will be using this random generated traffic. With that, as I said, we will find the starting point and end location of all traffic simulations, and we'll jump then into our optimized switches code, which implements an NCCC, or negative cost cycle cancellation algorithm. And this is the main portion of the E3MC paper. Basically, the NCCC algorithm is an algorithm used to route traffic from the source to the destination while minimizing the amount of power needed. The max power that a certain path can take is caused when we have to route traffic through a port and through a switch that are currently off. So the main portion of the NCC algorithm is locating what switches are on and following that path. That way we don't have to power them back on. After we've dedicated the NCCC algorithm to this process, we then go about looking at the exact paths for each traffic, and we analyze the power consumption. And we compare that power consumption to what a standard power is. So I'll start running this code because it does take some time and figures will pop up that I will explain, but also go into a little more detail of how things work. So I call run sim and I call 2N tree, which is just the original base network topology, which is this one. We start off with two core source locations, and as we move down towards the destinations, we increase the size of the tree by 2n. And we'll put a flag to use the Poisson distribution for the traffic generation. So basically the way that this algorithm works is we're going to loop over 30-minute increments throughout the entire day. So this process is going to loop 48 times. And in each iteration, there are 16 traffic signals that are going to be routed. So every time this figure uploads, this is a new iteration from a different 30-minute traffic period. And what this is showing is, based on the network topology for the 2N tree, we have two source nodes. So starting from the left-hand side is the origination of where the traffic is, and all the way to the right is the destination nodes. So as you can see, every traffic begins with either a node at 0, or excuse me, a node at 1 or a node at 2. That's just where the random generator decided to start those node or that source at. And then we go through the path. So since this is a 2N tree, as we would expect, most of the paths will go from, well, not most, all of them will go from one of the first 2 sources and then go to a 4-port network. So looking at the diagram, if we start off with 2 and we go one level further, we're going to go 2 to the second power, which will be 4 different ports, which is why there's 4 different options right here in the middle. And then switching over to the third path, which would be this edge location right here on this diagram, we can see that everything deviates into 8 different networks, and so on and so forth. So this is just showing the actual path and what switches each route takes. So to follow this orange line, for example, we start off at node 2, which is where we randomly generated that value, and it's going to end at node 14. So the NCCC algorithm found that the best path is to go through switch 2, then to switch 6, and then out to its final destination. So this is kind of just how the algorithm works. And I'll continue to let this run through, and then after all of the 30-minute simulations, the final results will be tabulated, and we'll be able to compare that to what the authors had, and also, more importantly, whether or not this NCCC algorithm and the entire E3MC simulation is beneficial, if it basically doesn't have much impact to the power, or if it actually has more power consumption to it. So we'll continue to run this, and once it's complete, I'll explain what the results show. And then after that, I will, instead of letting all 48 iterations execute for both the fat tree and the B cubed, I'll just start the simulation. That way you can see what the paths look like, and I can explain some of the issues that we came up with throughout this process. With the 2N tree, we didn't run into many issues because the traffic and the network itself is pretty easy, but as you get into these types of situations, things get a little more complicated when there's more options on which paths and switches you can use. While this continues to iterate, the biggest issue that we ran into when running the NCCC algorithm is the authors didn't explain what paths to take if there are multiple optimal paths. For example, if we were starting off at this core and we were choosing which level to go to, for example, where there's 4 different paths you can take, and more than one switch was turned on, the paper doesn't explain how to choose from those multiple on switches to choose which one. So we decided to randomly choose out of the switches that are turned on, or if they're all turned off, randomly choose which path to take. Now, not knowing exactly what the author did, this will explain one of the differences that we have compared to their results, but that's something that we would have liked the authors to explain rather than giving very brief details on how the NCCC algorithm works itself. So going back to the 2-tree database, the algorithm has completed, and this is our actual final power consumption. And this is a ratio between the power that we took compared to the power that a standard path would take. So a value of 1 would represent our E3MC algorithm executing and having 0 benefit compared to the power and energy needed for a traditional networking path. So as you can see, the results are pretty much flatlined right around 80%. And this is as expected when you look at the plots that were popping up after every iteration. They looked almost identical 30-minute cycle to 30-minute cycle. So after executing this entire tree and simulation, we're showing that if we use the E3MC algorithm, we'll save essentially 20% when it comes to power. So we were getting a benefit here. More results will be explained in the white paper, however. So let's close everything, and I'll rerun the software, but with the fat tree, so that you can see the differences. And where I was talking, we were getting issues with not knowing which paths to take. And as you can see, just looking at the printouts of how fast iterations are going through, some take significantly longer than others, and those are the ones where I'm running into loops that do cause issues. So as you can see, rather than 3 paths being taken, we're going all the way out to 13 or 14 for this iteration, which is not very ideal. However, most of the paths down here that start off at 0 and go all the way out to 10 and then jump up to 13, that's where most of the paths actually lie, because I'm plotting 16 different iterations. These ones out here are mainly outliers that couldn't find a optimal situation when having to randomly choose which path to take. So this is why some of our results may be skewed when it comes to the final results. However, out of all 3 different network topologies, we're still getting roughly that 20 to 25% increase or benefit, from the power consumption itself. So I will end this iteration really quickly, since the results are fairly similar. Everything will be shown in our white paper, and I will quickly run the B-cube situation. Now, comparing this to the fat tree, the B-cube is actually even more complex, so the number of iterations increases as well. However, the results do show that the B-cube does pretty much perform the exact same, if not slightly better, compared to the 2N tree, and that's still 25% better than the current implementations of how these work. So one other big change between our results and what the authors presented was they were using actual real-time data. Now, in their paper, they couldn't provide the real-time data that they were using. So every time we run our simulation, a Poisson distribution is generated for our traffic. This is not the same as how the authors used it. They did say that they had the capability of using the same distributions, but overall they wanted to display their real-time data to have better results and more accurate results. So it's just another delta between us and what the authors were. But on the benefit side, out of all 3 network topologies, we were able to decrease the amount of power needed in order to complete the task at hand. For more results and conclusions, please see our white paper that we have produced as well. Thank you.